Finally, the output wave shape would look like this. Okay, so the black line is our input signal and the red line is our output signal. And the green region is when the diode is on. That means the diode is conducting. The red region when the diode is off, when the diode is not non-conducting. Again, the green region is on. So that means when you have the capacitor connected parallel to the resistor, in that instant, the diode is not always on or not always off. You also notice the minimum value, this point is our V min, and this is our V max. So V min to V max minus V min. So although we have managed to make the difference between maximum to minimum with respect to the situation when there was no capacitor connected smaller, but still there is some difference. So this difference is called ripple voltage, VR. So ripple voltage. And the mathematical expression for ripple voltage VR into Vp over FCR. Here Vp is equal to the peak output voltage. So that can be Vm minus Vd, where Vm is the input maximum and Vd is the voltage drop across the diode. Now that we consider the diode is ideal, so that means Vd is equal to 0, which is Vm. Now in case we consider the diode is not ideal, that means we're going to replace the diode with 0.7 when it is forward bias. In that case, it would be Vm minus 0.7. So VR would be Vp divided by FCR. F is the frequency of the signal. C is the value of the capacitor and R is the resistor. Now we can change the value of VR by changing the value of resistor and the capacitor. So generally, if the value of C is higher or R is higher, so that means it is going to take a longer time to discharge. It is going to longer time to discharge. That means in that case, if C and R, both of them are higher, in that case, let's say it is going to take this path. So which means it takes longer time to discharge. So correspondingly, ripple voltage VR will be smaller. So that also agrees with our mathematical expression, which means if C is bigger, VR is smaller, R is bigger, VR is smaller. So by changing the value of R and C, we can minimize the ripple voltage. However, yet we still have ripple voltage. Now, in case we consider the full wave rectifier, in that case, as opposed to positive half cycle, we're going to have both negative half cycle as well as positive half cycle is rectified. And in that case, let's say we can include the negative half cycle in our rectification process. And in that case, the rectified signal, so let's say the rectified signal would look like this. If you start from here, So the green line is the rectified signal for full wave rectification. And again, maximum to minimum distance would be our ripple voltage VR. So notice the ripple voltage for full wave rectification and the ripple voltage and the half wave rectification are not same. So ripple voltage for full wave rectification is smaller than the ripple voltage for half wave rectification. So if this is the ripple voltage for half wave rectification and this is the ripple voltage for full wave rectification. So that means VR is clearly smaller here. In that case, VR would be Vp over 2FCR. Vp is again the peak voltage. Vp, in case we consider full wave bridge rectifier, in full wave bridge rectifier, for each cycle we have to pass through 2 diodes. You see, if this is a full wave bridge rectifier, for both positive half cycle and negative half cycle, we have to pass 1 diode, 2 diodes. So that means Vp would be Vm minus 2 Vd for full wave rectifier. How about if you consider full wave rectifier with center tape transformer? In that case, this is our circuit. So for each half cycle, we have to pass through 1 diode. So that means Vp would be Vm minus Vd. Full wave rectifier with center tape transformer. In that case, so that means the expression for VR for full wave rectifier will be this. Only thing will change will be Vp. So Vp for full wave rectifier would be Vm minus 2 Vd, and full wave Vp for full wave rectifier with center tape transfer would be Vm minus Vd.